Okay, so let's talk about a few examples of how do we calculate the VC dimension of certain classifiers. Let's start with something simple. What is the VC dimension of a 2D classifier with a rectangular shape? So think about that you have a set of data points that are allocated in the 2D space, and then we are going to draw a rectangle, and then from this rectangle we are going to say that anything that's inside the rectangle, it will be classified as +1. Anything outside will be classified as -1. And we ask, what is the VC dimension of this rectangle classifier? So let's start by looking at the case where you can have 4 data points, and you can put these 4 data points in whatever way you want. Now, what is the number of possible configurations? Well, you can calculate. There are 4 data points, and so they are binary, +1 and -1, and therefore you will have 2 to the power 4, which is 16 configurations. So you can draw all the 16 possible configurations, and I'm only drawing you how many? I'm only drawing you 4 here. Okay, so this is an illustration of what I mean by a rectangular classifier. Okay, so you can have you can have 4 data points that will be here. So you have 2 crosses at the top and bottom, and you also have a cross at here. Okay, so this is plus, and then now you have a -1 over there. We ask, can we try to draw a rectangle that can classify them into 2 classes? And the answer is yes, right? Because I can draw a rectangle at this shape, and anything inside would be classified as +1, anything outside would be classified as -1. Now you can also consider that case where you have a plus here, and then you have all the minus down there, so that you can also classify. Now, rectangular classifier is more useful than the linear classifier if you try to think about this example. Okay, so you have all the plus here. So okay, you can have the plus at the top, at the bottom, and then you can have the minus at the 2 sides. And if you only use a linear classifier, we see that you're not able to classify them. But since you're using a rectangular classifier, then yes, we can classify them. So we ask, for all these 16 configurations, will the rectangle classifier be able to classify all of these 16 configurations? The answer is yes, indeed. Why? Because for anything that you can classify using the linear classifier, the rectangular classifier, of course, can also do that. Now, how about the cases where your linear classifier are not able to handle? Well, as I'm showing you here, this rectangular classifier can also classify them. And therefore, you can think that the rectangular classifier is a little bit more powerful than the linear classifier. And therefore, as I'm showing you here, all the 16 configurations can be shattered by the rectangular classifier. Now, if you try to go with 5 data points, you can try to pick up a pencil and also put on a paper, try to put something, then you can see that it is not possible to shatter 5 data points. For example, I can put the 4 plus 1s at the diamond shape. So you have 1, 2, 3, 4. You have 4 data points. And then you also put another data point that's in the middle. And then the middle one will be -1, and then the 4 diamond will be the +1. In that case, you will not be able to shatter them. And therefore, we say that what is the number of the dichotomies that this rectangular shape can classify? The maximum number would be 4. Okay, and so what is the VC dimension? Well, the VC dimension is 4 for a rectangular classifier in a 2D space. So let's try to work on a more complicated example, which is the VC dimension of a perceptron algorithm. Hopefully, by going through this second example, we can gain additional insights of how do we calculate the VC dimension. So what is the VC dimension of a perceptron algorithm? It turns out that the VC dimension of a perceptron algorithm is D plus 1. Now, what is D? D is the input space of your input vector. So you have a D-dimensional input vector. And you also add 1 to that because you have a bias term. So the VC dimension is D plus 1, and we want to show that this VC dimension is indeed this number. And if we can show that, then we can sort of get an idea of what, how expressive is your perceptron algorithm. Is indeed not infinitely large, although the set of hypotheses is infinitely large. However, the VC dimension is only a finite number. And so as you run your Huffington inequality as n goes to infinity, this VC dimension should probably do not affect your generalization bound. So let's look into this results of what is the VC dimension of a perceptron algorithm. So the plus 1 comes from bias term, and also so the linear classifier is no more complicated than d plus 1. This is what this theorem is telling us about. The best it can shatter is d plus 1 in a d-dimensional space, and if d is 2, we can sort of show that the VC dimension is 3. Okay, so let's look at how do we prove. The proof consists of two parts, or two cases. The first case is that we want to show that VC dimension is at least d plus 1. And in the second case, we want to show that the VC dimension is at most d plus 1. If these two holds, then you can argue that, yes, the VC dimension, it can only be d because you want to make the two inequality to be satisfied. So what is the meaning of having the first inequality? VC dimension is bigger than d plus 1. That means we want the hypothesis set to shatter at least d plus 1 data points. Now, it may shatter more, or it may not shatter more. We don't know by just looking at this statement. Okay, so what the statement says is that you can shatter at least d plus 1. Now you can shatter d plus 2 data points, you can shatter d plus 3 data points. I don't care. In this statement, I just need to show that it can shatter at least d plus 1. The other side says that H cannot shatter more than d plus 1 data points. If I can show that, then since I also have the first inequality, then I can claim that it has to be d plus 1. Let's first look at the first case where I want to show that VC dimension is at least d plus 1. So what can I do? Well, what I need to do is really to come up with a configuration that has d plus 1 data points and that can be shattered by the H. So let's think about in the 2D case. So if you put the 3 data points anywhere, not on the same line, we will be able to shatter all these 3 data points. How about in the high dimensional space? Well, in the high dimensional space, we can consider a vector this is your data points, xn, this is your nth data point. And this nth data point, you have 1 in the first entry. This first entry denotes the bias term. And then you have another one that's somewhere in the middle. And so this is one of the D entries in your vector. And then you have a classifier. This is your perceptron algorithm. The perceptron algorithm says that I am going to calculate a W vector such that when you take the sign of this W transpose X, you will get to the label Yn. So what I can do is to consider the following equation. Now, in this equation, I have how many data points? I will have d plus 1 data points as I'm showing you on the right-hand side of this equation. You have all the y1 through yd plus 1. These are the labels. So you can have plus 1, minus 1, plus 1, minus 1, and so on. So if you look at this equation at the far right, I have plus 1 or minus 1. They can take any pair. Okay, so you can, for y1, you can take either plus 1 or minus 1. For y2, you can take plus 1 or minus 1. So by shuffling between plus 1 and minus 1, you will have a set of strings, and the number of strings will be 2 to the power d plus 1 in this case. Now let's look at the equation on the left-hand side. This is the perceptron algorithm. The perceptron algorithm says that I'm going to calculate a set of W's, and then I want to try to look at all my data points, okay, x1 through xn plus 1. So I have all these n data points, and then I want to calculate this inner product. Now you may ask, why do you want to choose all these numbers? How does this matrix come from? This matrix comes from the particular choice of the data points that I'm giving you here. Okay, so think about that. These data points would be the data points that you have the freedom to allocate. You can put the data points all on the same line, which will not be able to tell you the shattering behavior, or you can put the data points in different corners, and this is a specific choice of the configuration that I want to make them as orthogonal as possible. Now, as long as I can show that for this set of data points, my perceptron algorithm can actually shatter all these data points, then I'm in good shape. Okay? And so I just need to come up with one configuration of data points, and then I show that this equality will hold. So now let's look at this equality. This equality says that I want to take the sign of this matrix vector multiplication, because this matrix vector multiplication comes from your perceptron algorithm. Okay, so that is giving you the sign of the W transpose Xn, and since I have all these n data points, I will have this matrix equation. Now, then what I can do is that these data points, the locations, they are given by the choice of 1 and 0s. So here you can think that these are the locations. How about the plus and minus signs? The plus and minus signs will tell you different dichotomies. So if you choose all ones, then what you can do is that you can just put the classifier somewhere that anything that is lower than that, it will be classified as +1. Or if you want to have some +1, some -1, you just need to move your classifier in such a way that some of them are +1, some of them are -1. So that can be done by moving around the +1 and -1s. So what would be the allowable variables here? It would be that this matrix, of course, is given to you. It's a fixed matrix. That is the location of the data points. The y's is also fixed. They are the labels of all these data points. We ask, are we able to generate this dichotomy if you give me the +1 and -1 according to whatever way that you are defining? So then we ask if we can ever come up with the W0, W1 all the way to WD. These are the variables. If I can ever solve this problem, then that means I am able to generate a linear classifier that comes out from this perceptron algorithm such that I can shatter all these D data points. So to calculate this result, we can try to remove the sign, because what we want to do is just to come up with one possible configurations that you can shatter the data points. Okay, so the sign, of course, will tell you the +1 and -1s. Okay, so now, so then you can choose different W's, but I do not need to enumerate all the possible W. I just need to come up with one W such that this equality will hold. Okay, instead of putting a sign there, the sign says that if you have different types of W's, you have different W0, W1, WD, you have different configurations of the W's, you may have multiple W's that can give you the same +1 and -1. But I don't care. I just want to come up with one particular choice of the W's such that I can make all the numbers to be +1 and -1. This W is not a perfect W. It's not a good W. It's not an ideal W. I just want to show that there exists a W such that I can make this equality to hold. If I can make this happen, then of course if we put a sign outside, that will also hold. And so we are only interested in whether the problem is solvable. We are not interested in finding the optimum W. And so we just need to see if we can ever find a W such that we can shatter all these D+1 data points. If there exists at least one W that can make all the +1 and -1 correct, then we can claim that it is shattered, if you can use that particular W. So that question boils down to whether this D+1 times D+1 system of equations is invertible. And clearly this is invertible because this matrix here is an invertible matrix. You can put into your computer and try to calculate that this is an invertible matrix. And so you can show, since it's invertible, then for whatever the +1 and -1 that you give me, whatever combinations of the +1 and -1 you give me, I will be able to tell you the W's. And therefore, I should be able to shatter all these D+1 data points. So now, let's work on the opposite case where we want to show that the VC dimension is at most D+1. So we ask, can we shatter more than D+1 data points? Then the answer is no. And what can we do is that you only have D+1 variables. And then now if you have D+2 data points, that means you have D+2 equations. then one equation will be either redundant or contradictory. If it is redundant, you can ignore it because it's not the worst case yet. But if it is contradictory, you cannot solve the system of linear equations. Okay? And so you cannot shatter more than d plus 1 data points. So let me just summarize what was happening here. If you have more than d plus 1 data points, let's say your d2 plus 2 data points, what will happen to your equation is that you will have one more line of equations. And that one has to be depending on the previous d plus 1 rows of your matrix. And if that happens, it has to be either redundant or it creates a contradiction to the previous d plus 1 rows. And if that happens, then you cannot shatter the d plus 1, you cannot shatter the d plus 2 data points. And therefore, the maximum number of the data points that can be shattered in this case would be at most d plus 1. You cannot do more. Okay, so suppose we let's take into look of all these vectors. Suppose you have x1 through xd plus 2. I can always write the x of d plus 2 as the summation of the previous d plus 1 variables. Because I do have the d plus 1 variables here, and so I can write d plus 2 as a combination of the previous ones. And so not all AIs are 0, otherwise it would be a trivial problem. And so my job is to come up with a dichotomy which cannot be shattered by any of h. And here is a dichotomy. Okay, so let's say your x1 through xd plus 1 will get the yi equal to the sine of all the AIs. Okay, and then the x of d plus 2 will give you yd of plus 2 equals to the minus 1. And now you go back to the equation here. If all the y's they are the signs, and then the last one is minus 1, then you will not be able to construct. You will not be able to shatter the data point of d plus 2. Okay, so what will happen is that if you take the W matrix, take a W vector on this d plus 2, then on the right hand side, you need to multiply this a summation of AI and W transpose on Xi. And the perceptron algorithm says that the sign of the W transpose Xi is the Yi's. So by our design, Yi is the sign of the AIs. So what will happen? Well, the AI times the W and Xi, it has to be positive. Why? Because the W transpose the Xi has to be a number that is the sign of the A. If that's the sign of the A, you also have another A here. And so the A multiplied with the sign of the A, that will give you a positive number of the A. Okay, and so that would be always positive, and so that forces the summation of the AI and W transpose Xi to be positive. And therefore, what is the Y of d plus 2? Y of d plus 2 will become the sign of the W transpose of xd plus 2, and that has to be plus 1, and that would be a contradiction. So we find a dichotomy which cannot be shattered by any h, and therefore we claim that the VC dimension cannot be bigger than d plus 1. So to summarize, what we have shown before is that if you have a positive array, then the growth function is n plus 1, and we can show that if you only have one data point, the growth function of mh of 1 is 2. And then if you have two data points, the growth function is 3, and 3 is of course less than 2 to the power 2, which is 4, and so we claim that the VC dimension is 1. What about if we are looking at the positive interval? Well, the positive interval has this equation of the growth function, and we can say that what if n is 2, then the growth function is 4. Okay, and that is 2 to the power 2, and so then you can shatter. How about n equals to 4? Well, if n equals to 4, you show that the growth function evaluated at 4 is 5, and so that is less than 2 to the power 4, which is 16, and so you claim that the VC dimension is 2. How about if the hypothesis set is a perceptron algorithm in d-dimensional space? We just show that the VC dimension is d plus 1. If H is a convex sets, then we show that the growth function is 2 to the power n, and no matter what n we choose, we can always show that the mhn of the growth function is always 2 to the power n, and therefore the VC dimension is infinity, and therefore the model is as complex as it can be. Okay, so here is the reading list for this lecture. I encourage you to take a look at these 3 references. Now, I also want to point you to an appendix of this lecture, which will give you another theorem. It's called the Radon Theorem. That gives you another way of proving the Perceptron Algorithm's VC dimension. So you can take a look at this theorem. So we resume the class in the next lecture. In the next lecture, we will talk about more on this generalization bound.